All right, welcome to the lecture covering 2.6, Other Types of Equations. Let's go ahead and get moving. This is actually going to be review material for you. And if you have not found it yet or explored around in our D2L section enough yet, in D2L, I have some links to some YouTube videos and some playlists that cover prerequisite material for you. So this is actually going to incorporate some of what's in those videos, but just using that information to actually solve equations. And if you look at our lovely little lizard meme here that I'm sure you've never seen before because I'm so original that way, you know that whenever you're thank you for the laugh, Josh. I'm glad that you picked up on the fact that that was dripping with sarcasm. Whenever you are solving an equation, you are always, no matter what type of equation it is, trying to isolate the variable raised to the first power. So we're going to look at doing that with a bunch of different types of equations just to kind of jog your memory on all this stuff. Okay, so the first types of equations that we encounter in this particular section are involving rational exponents. And if you dig way back into the depths of your memory, you will know that any rational exponent, as in a, some value, some base, raised to the m over the nth power. So it's raised to a fraction. Well, because whenever we raise a power to another power, we multiply, we can actually split that numerator off so that you'd multiply those fractions back together. So for example, off to the side over here, 1 over n times m over understood, let me get a different color, over understood 1 there. Well, when I multiply fractions, I multiply straight across, so that's just m over n. So this second way of writing this, notice there's an equal sign between every single one of these. These are the exact same thing. So since multiplication is commutative, no matter if it's fractions or not, and I know fractions is an F word to students, but it doesn't matter what you're multiplying, multiplication's commutative. That means you can flip-flop its position and it's still going to come out to be the same thing. In other words, 2 times 3 is the same thing as 3 times 2. So if we look here, that says that 1 over n times m is the same thing as m times 1 over n. There's no difference in these two things. Now here's the big kicker. And that is any rational exponent, so that's just a fractional exponent, can be turned in to its radical equivalent. So let me point this out, write it a little bit bigger. I always have a base, and if it's raised to a rational exponent, that is power over root. In other words, if I have x to the 2/3, that is the same thing as x squared, there's the power, and I'm taking the cube root of all of that. So that's what those next two, that's why they're written there, because you're expressing the same thing no matter if you say x to the 2/3 or the cube root of x squared. So let me stop here and just say, give me a green check if this background information makes sense before we move into actually working with these things. Y'all remember where the green check is? There's that drop-down menu over your names. Okay, Josh found it. Shayla, you all right with what I just said? Welcome, by the way, Shayla. Shayla, are you with us? I don't want to leave you behind if you're not understanding. All right, Shayla must have stepped away. Let me go ahead and clear that out. Okay, so another rule that comes up on this page that is prerequisite material is anytime I'm raising a base to a negative exponent, that is as if I had moved that power or that exponent from the numerator down into the denominator, and when I do that, my exponent becomes positive. And it works vice versa too. So let's say I start out with 1 over a to the negative nth power. If I bring that up to the numerator, that power becomes positive. So when I'm teaching this as a concept, what I always tell my students is a negative exponent's never happy. It always wants to be in the other position than where it is. So if it's upstairs, bring it down to the basement of the party. If it's in the basement, bring it on upstairs. It's partied too much. So it always wants to be in the other place that it is, and that's how the exponent becomes positive. Now that is not magic. It has to do with complex fraction or compound fractions, but I don't have time to go there with this, and just trust me on it. Or go watch a YouTube video if you want to understand how that happens. All right, so let's go ahead and look at these 3 examples here. 64 to the negative 1/3 power. Well, the first thing that jumps out at me is the fact that I have a negative exponent hanging out here. This is living in the numerator. It is not happy there. So I'm going to go ahead and bring it on down to the basement of the party. And that ends up giving me 1 over, when you cross the line, you leave 1 behind, 1 over 64 to the 1/3 power. Now, I like to change to roots. My brain works in roots much easier than rational exponents for some reason. So with this one, I am going to change that to 1 over the cube root of 64, and it's raised to the understood first power. So the cube root of 64 is 4, because 4 times 4 is 16 times 4 is 64. So what I end up getting is 1/4 here as my answer. Now, let me show you another way you could have thought about this same problem if you don't want to deal with roots and want to stick with rational exponents. Whenever I can change a number, let me just put a little divider here. Whenever I can change a value to its exponential form and I'm dealing with roots, do it. So this is the same thing as 1 over. Okay, so I can call 64 a number of different things to make this easier. But its most basic exponential form is 2 raised to the 6th power, I believe. Let me just check that on my calculator here. 2 to the 6th is 64. Yeah. So I could call this 2 to the 6th that has been raised to the 1/3 power. When you multiply fractions, you multiply straight across. So this is the same thing as 1 over 2. 6 times 1 is 6. Understood 1. Let me write in the understood 1 there. This is 6 over 1 in its fractional form. So, God, that looks terrible. Let me fix that. That looks like it's just a blob. All right. So when I multiply 6 over 1 times 1 over 3, I get 6 over 2, which is the same thing as, 6 over 3, which is the same thing as 2 squared, which is the same thing as 1/4. Doesn't matter which way you do it. You're going to end up with the same thing. If you don't end up with the same thing, you've done something wrong. Y'all good so far? Just a green check or a red X? Shayla, I need to make sure that you, okay, where's your question, Shayla? You can either type it into the chat window or you can click on the talk button and ask your question over the microphone. And I see you're typing, Shayla, so I'm just going to wait to see what you have to say. And don't ever be afraid to ask a question in these lectures. This is why I invite students. Oh, no question. Okay, good. So you just meant to hit the green check. But let me just say this. This is why I invite students to come to these recordings, because if you've got the question, more likely than not, 10 other people that are watching this video have the same question you do. So ask as many questions as you need to ask. That's what you're here for tonight. All right, so that is evaluating a rational exponent expression. And now let's look at solving an equation. So we have x to the 3/2 power equals 125. Well, I can either turn this into its equivalent radical form, or I can work with the rational exponents. And I believe with this one, I'm going to choose to work with the rational exponents. So if I multiply this entire side by 2, which is really a 2/1. I'm sorry, if I raise it to a 2, I have to raise this side as well, so I need to square that side. I wrote the left side as fractional because I'm working with fractions on that side. When I multiply fractions, I multiply straight across. So 3 times 2 is 6. 2 times 1 is 2. And now 125 squared, I'm going to have to go to my calculator for that because I don't know that off the top of my head. 15,625. Now notice what happens with that rational exponent. Because I chose to multiply by its denominator, I knew that I was going to create a value that would simplify to an integer. So 6 divided by 2 is just 3. So the trick here, watch this. Look back up at that first line where I multiplied, or where I squared both sides. 2 divides by 2. Let me get a blue to do that. 2 divides by 2 here. So I'm just left with 3/1, which is just 3. So if you multiply a fraction by its denominator, you're always going to end up with an integer. So now I have x cubed is equal to 15,625. Now, when I want to undo something that's been cubed, I take the cube root, because cubing and taking the cube root are inverse operations of each other. So I take the cube root of both sides, and the cube root of anything cubed is just that thing. And then I'm going to go to my calculator, and if you, do either of y'all have your TI-83 or 84 calculator handy? Because I can tell you where to find the cube root. Okay, all right, so if you will click all the way over on the left-hand side of your calculator is a math key. Go ahead and press the math key, and the very first list that comes up, the fourth choice down is the cube root. And so I'm going to go ahead and click on that, and that brings me back out to my screen and puts the cube root there. So 15,625, and the cube root of that is 25. So that's it. And you really should check it by plugging it into the original equation, but I don't want to waste too much time tonight so that we can make it through this lecture in a timely fashion. All right, so this third, by the way, did both of y'all print out the note sheets? Because I'm going through them right now. And it will really be helpful if you're filling those out while you're participating in the lecture too. Okay, Shayla did. Josh, did you get a chance to print those out? Okay, no worries. I would just encourage you to be working this on your own paper, Josh. You know how I teach. You've been in my class plenty, so okay, good deal. All right, so here again we are faced with a rational exponent, and we're trying to get to that x on the inside. So notice I have, let me just rewrite this. See, x plus 5 to the 3/2 power equals 8. Notice I have a 2 in the denominator of my exponent, so that's what I'm going to raise both sides to. Because my 2's divide out here. And now all I'm left with on the left-hand side is x plus 5 cubed. And 8 squared is 64. Taking the cube root again of both sides. To undo the cube, I take the cube root of anything cubed, I'm left with just that thing. And the cube root of 64 is 4. Cube root is asking what can I multiply by itself 3 times to make 64, and that's 4. And now I'm left with a sweet linear equation. These are the types of equations that you wish all of them looked like. So I'm just going to subtract 5 from both sides. And x is -1. Green check if you're good to move on from these types of equations. Red X if you've got questions. Shayla, you good? Okay, great. Okay, polynomial equation. Whoop, I hit it twice. Once too many. There we go. Polynomial equations. Now, don't let this nasty thing in the center here scare you in this gray box. This is just the definition of a polynomial here. You start a sub n is your leading coefficient. So all a sub n is standing for is that very first coefficient that you get to when your polynomial is in standard form. N is equal to the degree of the polynomial. And you know the degree is always the highest exponent. So it's going to come first when you put it in standard form. Now, it should make it easy to understand why we would call the next one down n minus 1. A sub n minus 1, so that's just the coefficient on the next term down. And notice the exponent's going to be 1 down from the degree. So you just step your way all the way down to x squared. A sub 1x to the understood 1. A sub 0. A sub 0 is just your constant, or just your number hanging on the end there. So green check if that definition makes sense now. Okay, Josh, I see you're typing. I'll wait to see what you have to say. Okay, all right. So you can look at this part of the explanation here. N is a positive integer. So a sub n steps all the way down to a sub 0, and those are your real number coefficients. And then the x's are just standing for your variables raised to descending powers, going down. So it's just a naming system, basically, saying the first term that you get to in standard form, the second term, the third term, that type of thing. So whenever you're solving a polynomial equation, you have to set the equation equal to 0 by rearranging the terms, either adding or subtracting them off of both sides. Reason being is the way you're going to solve polynomial equations, you're going to first set equal to 0. The second thing you're going to do is factor. Oh, there's another F word for you. Factor the polynomial. And what you're going to end up with are things that are being multiplied that equal 0. Once you factor it, you're going to have this times this. And so you've got things that are being multiplied together equaling 0. Well, this allows us to use what we call the zero product property to solve. What the heck is the zero product property? The zero product property says if I'm multiplying things together that equal 0, then I had to know that either A equaled 0 and or B equaled 0, because the only way to multiply and make 0 is to multiply with 0. So I think this will make a little more sense when you see me go through it here. Let's start with this first one. We have 12x to the 4th equals 3x squared. My first task is to get this equal to 0. So I am going to subtract 3x squared off of both sides. And that leaves me with 12x to the 4th minus 3x squared equals 0. Now, my second step, factor the polynomial. So I have a GCF that I can take out of both of these, and the GCF that I see is 3x squared. They each have a 3 in them as a factor, and they each have at least 2 x's as a factor. So when I factor this using GCF, I divide each of my original terms by my GCF and see what I'm left over with. It's reverse distribution is what it is. So now I'm asking myself, what would I have to multiply 3x squared by to make 12x to the 4th? Well, that's 4x squared. And what is negative 3x squared divided by positive 3x squared? Well, a negative divided by a positive is a negative, and that's just 1, because anything divided by itself is 1. So now I've got my polynomial factored, and I've got it equaling to 0. I am now ready to apply my zero product property that says if we have this situation where A times B equals 0, then A had to equal 0 and or B had to equal 0. That's exactly what I'm going to do. I'm going to say, well, if this is the case, and I'm multiplying them together to make 0, then either 3x squared had to equal 0 or 4x squared minus 1 had to equal 0. Now, I still have to solve these, but I've made my task much easier. With this first one, all I need to do is divide both sides by 3, and I'm left with x squared is 0. Take the square root of both sides to undo that square, and I get x is equal to, normally we would have to consider the positive and the negative values that multiply to make 0, but 0 has no sign, so it's just x is 0. There's one of my solutions. Okay, If you're rusty on your factoring, this one may blow your mind here for just a moment, but bear with me. This is a difference of squares. It's something squared. Here, I'll write this off to the side. Can't not explain it. Something squared minus something squared. And whenever I have that particular situation, which my somethings are 2x and 1, whenever I can force my polynomial into that mold of something squared minus something squared, it is a difference of squares, and it factors as my a term plus my b term multiplied by my a term minus my b term, and that equals 0. Now I'm to the point of being able to use my zero product property again. You see I have something multiplied by something equals 0. So here I either have 2x plus 1 equals 0 or 2x minus 1 equals 0. And now I just solved the linear equations here, which y'all could probably do blindfolded on one foot. Subtract 1 from both sides. That's what I'm going to add 1 to both sides. And this is 2x is negative 1. I'm going to try to make it on the page here. Divide by 2. I'll have to write the answer off to the side there. So for this one, x is negative 1/2. And here I have 2x is positive 1. Divide both sides by 2. So x is 1/2. I have 3 solutions to this one problem. In other words, I can take any of these solutions, plug them back into the original equation, and I will get a true statement. Which is crazy to think about. So 0 works. You can do that in your head pretty quickly if you look back up at the original equation. I also have negative 1/2 and positive 1/2. So 3 solutions. If you wanted to write them as a set, it would be x equals the set 0, negative 1/2, and positive 1/2. Some set notation there. Okay, so same type of equation, polynomial equation for b, but we're going to be using a different factoring method. So we've got 4 terms. And whenever you have 4 terms that you're going to try to factor, bells and whistles should go off in your head to use grouping. So I'm going to walk you through that. To group, you split it down the center, and you GCF your first 2 terms. So my GCF here is a 3x squared. My leftover is x minus 2. Move to the opposite side. Pull a GCF out there. 27 is a factor of 54. So I can pull out you never want to leave a negative leading term, so I'm actually going to pull out a negative 27 to get rid of that negative on the leading term on the second side. And I'm left with x minus 2 equals 0. So now, all I'm going to do is rewrite this so you can see something here. So I have 3x squared times x minus 2 minus 27 times x minus 2. And that equals 0. Okay, so what I'm left with, and this will always happen when you use grouping, I'm left with what I call a big binomial. A binomial is a 2-termed polynomial. I have 1 term here, and then I have 1 term here. They're just made up of nasty-looking factors, those terms are. So there is a common factor between both of these terms, and that common factor is x minus 2. That becomes my new GCF of my big binomial. So I pull that common factor out front, and when I divide that common factor out of each of the terms, I'm left with 3x squared minus 27 equals 0. So now I'm back to the point where I can use my zero product property. The zero product property says, well, if you are multiplying things together that make 0, then something had to be 0. The only way. So this one's easy on the left. X is equal to 2. Wham, bam, done. You go ahead and box that in as a solution for you. And then we have whatever's happening on the right here. I've got another GCF. I've still got a polynomial. So my GCF is 3. When I divide that out, I get x squared minus 9, which is a difference of squares, just like we had right there. So this is 3 times x plus 3 times x minus 3 equals 0. By the way, I've got an entire playlist of YouTube videos that I actually made just on the different methods of factoring. So if this is freaking you out, don't worry. Just go brush up using those videos. Okay, now I've got 3 things being multiplied together that equal 0. So I need to apply my zero product property. Well, 3 does not equal 0. It never has, it never will. So you don't have to worry about the 3. You can just ignore it. But x plus 3 could be 0, or x minus 3 could be 0. So here x is negative 3. Here, x is 3. So I have 3 solutions again. And Josh, I see you're typing something, so I'm just going to box these in and write my solution set while you're finishing up. X equals the set 2, negative 3, and 3. And I'm just going to wait to see what you have to say, Josh.
Hey, I just realized I was the only one on here.
Yeah, you're welcome to use
sorry.
a microphone.
Okay, so I'm in the library right now, and my computer's about to die, and the little end piece that like plugs into the wall for my box is not on my charger for some reason, and
So are you about to leave the lecture?
yeah, I think that's what's going to have to happen.
Okay, yeah, no problem. Now, Josh, if you are interested in hearing the rest of the lecture, you can join in on your phone, but don't feel obligated because I know it's pretty annoying to try to watch a screen like that on your phone. But you can join by phone. You just have to download the Collaborate app.
Oh, okay.
But like I said, don't feel obligated. I mean, these aren't even mandatory lectures. So, you know, I just appreciate you trying to be here and being here as long as you have been.
Yeah, I mean, I really everything kind of came together at once, but okay, so you're just going to continue the lecture?
Yep, I'm just going to keep on keeping on because I'm recording this to post for everyone. So I'll record a lecture whether anybody's in the room or not.
Okay, well, I'll just watch it after you do it.
All right, well, I will be so sad when your computer dies and you're not in the room anymore. Thank you for coming tonight, Josh.
All right, and I will be, I'm going to make the 7:30.
Okay, cool. I'll see you back here then in a little while.
Okay, perfect.
All right, see you soon.
All right, bye.
Bye. Okay, radical equations. we've actually already seen a little bit when we were looking at rational equations. I'm sorry, not rational equations, but rational exponents. Okay, so how to, okay, an equation is a radical, it's considered a radical equation when it skateboards and comes from the 1980s. And it's really radical. No, I'm sorry, that was a really terrible joke, and I will make sure to rework my material before I take it on the road. It's an equation where the variable lands under the radical sign, which when anything is sitting under the radical sign, it's called a radicand. So whenever you have a variable living up underneath a radical, you're dealing with a radical equation. Okay, so how do we solve these? The first thing you want to do is isolate. Now it says isolate the radical expression. You could have more than one radical expression. So I would add in here isolate one of the radical expressions on one side of the equal sign, so on one side of the equation. Put all your other terms on the other side. If the radical is a square root, you're going to undo a square root by squaring both sides. If it's a cube root, you're going to cube both sides. So the rule is for the nth root, you're going to raise both sides to the nth power. And doing so eliminates that radical symbol. Solve whatever type of equation you're left with. You may have lucked up and get left with a linear equation. You may have a quadratic equation once you do that. So it all depends on how it works out. I believe you, Josh, and I don't only believe you, I know you're going to make an A in this class, and I will see you at 7:30, man. I feel like I should be playing taps on the bugle while your computer dies. Okay, so if you have a radical that still remains, you've got to repeat this process, and I've got one of each type to look at on the next page. Oh, and also, whenever you're solving radical equations, you always want to check them because you can end up with extraneous solutions. So let's go ahead and move forward. All right, so we will start out, and just lost Josh. We will start out with the square root of x plus 3 equaling 3x minus 1. Now, our first step was to isolate one of the radicals on one side of the equation. And we're already isolated here. So, because the only thing that's on the left-hand side of the equation is the radical expression. Since it's a square root, to get rid of the square root, I square both sides. Whenever I square a square root, I'm left with just that thing. And then on the right-hand side, I'm going to write this out because most students miss this whenever they have a binomial squared. They miss that middle term. This is actually 3x minus 1 times 3x minus 1 that you're going to have to do distribution to expand it into a polynomial. So I'm going to multiply here and here and here and here. So I still have the x plus 3 hanging out. And now I have 9x squared minus 3x plus 1. And now I have the polynomial equation. And we already have looked at how to solve polynomial equations. We got to get it equal to 0. And I have like terms that I can combine as well. So I can combine these like terms. And I'm going to go ahead in this same step, and I'm going to subtract x from both sides and subtract 3 from both sides to get that left-hand side equal to 0. It doesn't matter which side equals 0 because anything always equals itself. That's a reflexive property. But so just do whatever is easiest for you. 9x squared. Okay, so I had a negative 3x, a negative 3x, and a negative, understood, 1x. That's negative 7x minus 2. Okay, let's see. It does not look like this trinomial factors. And so whenever you have a quadratic equation, you can always default to using the quadratic formula to solve. So I'll just write at the top the quadratic formula. X equals, because you're actually solving the equation, opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's what I'm going to use to solve this equation. And I'll just point out, oh, this comes from ax squared plus bx plus c. A always goes with my x squared term, so my a is 9. B is always my x term, so that's negative 7. And then my c is negative 2 here. So when I plug those into the quadratic formula, I get x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And then I just simplify from there. So x equals 7 plus or minus the square root of 49 plus, let's see, what is that, 36 times 2, which is 72, over 18. X equals, okay, so let's see, 49, oh no, my calculator just said low battery, gonna die. 7 plus or minus the square root of 121 over 18. X equals 7 plus or minus 11 over 18. And then we've got two solutions to worry about, the plus and the minus. So I guess this actually would have factored. I was just crazy in my head. Let's see, 18 times 6. Oh, 9 and 2. Oh my gosh, this would have factored so easily and it would have been much easier than this. But it was good to look at the quadratic formula there. So here we have 7 plus 11 over 18, which is 18 over 18, which is 1. And then we have 7 minus 11 over 18. 7 minus 11 is negative 4 over 18. And that reduces to negative 2/9. Okay, so let me just point out something that you have to be careful about. When you're taking a root, so our original problem has a root in it. When you're taking a root of an expression, you need to be taking, well, when you're taking the square root, it needs to be a positive number that you're taking the square root of, because if you take the square root of a negative number, you end up with an imaginary number. However, the only one that's in question, I'm okay with 1, because 1 plus 3 is 4, and the square root of 4 is 2. The one that's in question is negative 2/9. However, I'm adding it to 3, and so that's not going to be a negative number. I'm actually going to be taking the square root of a positive number there. So both of my solutions that I found are fine. And hopefully I'll have enough room to work this other one, because this one's a little bit of a doozy. So the square root of 3x plus 7 plus the square root of x plus 2 equals 1. All right, so I do have to isolate one of my square roots before I can square both sides. So I'm going to subtract the square root of x plus 2 minus the square root of x plus 2. So it goes away there. And now I have the square root of 3x plus 7 equals 1 minus the square root of x plus 2. And here's why I said that this one is a doozy. Because I need to square both sides. And look at that right-hand side. Yuck, yuck, yuck. Left-hand side's good. When I square root, that goes away, and I'm just left with 3x plus 7. However, this right-hand side is 1 minus square root x plus 2 times 1 minus square root x plus 2. Not my favorite thing to do on a Thursday night, but we'll make it. 3x plus 7 is equal to, okay, I've got a bunch of distribution to do here. I need to go here, and here, here, and here. All right, 1 times 1 is 1. 1 times the negative square root of x plus 2 is negative square root x plus 2. And then I'm coming to the inside. The negative square root of x plus 2 times 1 is negative square root x plus 2. Then I have the negative square root of x plus 2 times the negative square root of x plus 2. So that is the positive square root of x plus 2. Since it's multiplied by itself, it's squared. Which, thank goodness, because that gets rid of that square root there. So that's all I'm going to do in this next step. I'm going to do 2 things. I'm going to combine my like terms here, and I'm going to square that square root so that it goes away. Here's what I'm left with so far. Let me just give a little barrier between these 2 problems. Okay. So I have 3x plus 7 equals 1. Okay, the negative square root of x plus 2 combined with the negative square root of x plus 2 says I have negative 2 square roots of x plus 2. And then when I square the square root on the end here, I'm just left with x, so positive x and a positive 2. Oof. Now, I'm back in the position that I was in at the beginning with having a root in my equation. This is why, let me go back a slide. This is why I added in, you have to isolate one of them, go through the process, and then you're going to have to isolate the other one that may still be left after you go through that process. So that's what I'm about to do is isolate. Let me underline it so it sticks out to us. I'm about to isolate my root. So to do so, I'm going to subtract 1, subtract x, and subtract 2 from both sides. Minus 1, minus 2, and minus x. So it goes away here, here, and here, and transfers to the other side. So 3x and negative x is 2x. 7, negative 1, and negative 2 gives me positive 4. And that is equal to negative 2 square root x plus 2. However, it's still not isolated. It still has that factor of negative 2 holding on to it. So I'm going to divide both sides by negative 2 to get it off of there before I square it again. Okay, so 2x divided by negative 2 leaves me with negative x. Positive 4 divided by negative 2 leaves me with negative 2. And then I have the square root of x plus 2. Now I'm ready to square both sides again. My goodness, I can't believe how late it already is. Okay, so on the right-hand side, when I square root, it just goes away. This left-hand side is negative x minus 2 times negative x minus 2, and the right-hand side is just x plus 2. I have to do distribution again. I didn't think that this lecture was going to take this long. These problems are involved. Negative x times negative x is positive x squared. Negative x times negative 2 is positive 2x. Negative 2 times negative x is positive 2x, and negative 2 times negative 2 is positive 4. And then I have x plus 2. I've got like terms in the center here. And I'm going to go ahead and subtract the x and subtract the 2 because I've got a polynomial equation again. Minus x minus 2 goes away there to equal to 0. Okay, so x squared. I have 2x, which is 4x minus x. That does not look like a 2 there. Let me redo that. X squared. Okay, 2x, 4x minus 1x is positive 3x. And positive 4 and negative 2 is positive 2, equals 0. You could use a quadratic formula, but this factors. I don't have room to show you the factoring, but it factors as x plus 2 times x plus 1 equals 0. So that means, let's see, we'll come up over here. That means either x plus 2 equals 0, which in that case, x is negative 2, or x plus 1 equals 0, and in that case, x is negative 1. I need to look up top and see if I plugged either of these values in, am I going to end up with a negative value under the root, and I won't. So these are both considered solutions. So my solutions here, I have x is negative 2 and negative 1. Shayla, you good so far? All right. Okay. Absolute value equations. So real quick, a general note about absolute value equations. If the absolute value of x is written as absolute value sign with the x in the center, then it has the following properties. If x is greater than or equal to 0, then the absolute value of x is equal to x. If the absolute value of x is less than 0, then, if x is less than 0, then the absolute value of x is equal to negative x. In other words, if I say, what absolute value would I have to take? Now, that was a bad way of putting it. Let's see. That's a really yucky explanation of that. Because, let's see, okay, let's see. So, if I have the absolute value of x equals 4, since absolute value is talking about a distance, it's talking about a distance of a distance that a value lies from the origin on the number line. What that equation that I have written in orange there is saying is what value, that's the x part, what value lies a distance of 4 away from the origin. So we actually have two values that end up lying a distance of 4 away from the origin. We have the value in the positive direction, which is 4, because 4 lies 4 units away from the origin, or we have the value in the negative direction, which is -4. So hopefully that clarifies why they have this, because most students are like, well, every time you take an absolute value, it's supposed to be positive because it's talking about a distance, and that's true. But you kind of have to flip your thinking when you are working with an equation and go back to what is the question asking you. So this question right here is asking, what value lies a distance of 4 from the origin? Hopefully that was helpful. And Shayla, I do see you're typing something, so I'm gonna keep on going. Okay, here we go. Got it. Oh, no worries. Thanks for coming tonight, Shayla. I appreciate your attendance. I'll just finish up here. Okay, so for real numbers A and B, an equation in the form of the absolute value of A with B being greater than or equal to 0 will have the solutions A equals B or A equals -B. That's what I just explained above. If B is less than 0, then the equation has no solution. So consider this equation. What if we have something like the absolute value of X is equal to -4? This is saying what values on the number line lie a distance of -4 from the origin. Well, there's no such thing as negative distance in this reality that we are experiencing. So this has no solutions. So when you are setting an absolute value equation up, what you do is you pull your absolute value, the expression that's on the inside of your absolute value out, and you set it equal to the positive or the value in the positive direction and the value in the negative direction. So you're actually going to be solving two equations when you set up an absolute value equation. And don't forget that if that thing is equaling a negative value, there are no solutions to it. You can't take an absolute value and get a negative value out. Okay. And this is where it says set up both of those equations right there that I just told you about. Okay. So I have the absolute value of 1 minus 4x plus 8 equals 13. I'm going to isolate my absolute value by subtracting 8. I have the absolute value of 1 minus 4x equaling 5. I'm still good there. I'm not equaling a negative value. And now I set up the distance in the positive. This says, this particular equation now sets what value, that's the x, what value can I multiply by -4, add 1 to it, and land a distance of 5 from the origin. That's what that equation says. So I need to set up that distance in the positive direction and the negative direction. So I have 1 minus 4x equals 5, or 1 minus 4x equals -5. So I just solved these simple linear equations here, subtract 1 from both sides. I'm also going to subtract 1 from both sides here. And I have -4x equals 4, -4x equals -6, and divide by -4. and I get x is equal to -1 or x is equal to positive 3/2. Either of them will work. So x is equal to either -1 or 3/2. Now let's look at this next one. I have the absolute value of 2x plus 1 minus 2 equaling -3. So I am going to need to isolate by adding 2 to both sides. And when I do so, I end up with the absolute value of 2x plus 1 equals -1. This question is asking, what value, that's the x, what value can I multiply by 2 and add 1 to and land a distance of -1 from the origin? There is no such thing as negative distance. So there are no solutions to this equation. Or you can write the symbol for no solution, either or. Okay, quadratic form. We've actually already gone through quite a bit about quadratics, so this should be fast. I've got 2 slides after this, Shayla. I appreciate you hanging in there for as long as you have. I apologize, we're over an hour. A general note, quadratic form. If the exponent on the middle term is 1/2 of the exponent on the leading term, we have an equation in quadratic form, which we can solve as if it were quadratic. We substitute a variable for the middle term, solve the equations in quadratic form. Okay, given an equation, quadratic in form, solve it. First you want to do is identify the exponent on the leading term and determine whether it is double the exponent of the middle term. If it is, then you can use this method. So if it is, you're going to substitute a variable. Usually we use u to substitute in as a variable for the portion of the middle term. Write the equation so that it takes on the standard form of the quadratic using one of the usual methods for solving. And the methods that we have for solving a quadratic are the square root property, the square root property only works if there is no bx term, so no middle term, which none of these are going to come up as that. We also have factoring, and then using the zero product property, like we have been, or we have the quadratic formula. And you've seen both of those, actually you've seen all 3 of these used in this lecture. So once you get done solving it, then you replace what you substituted with that original term and solve the remaining equation. So let's take a look. I think we've only got, I know we do have 2 of these. Okay, so notice we have x to the 4th minus 8x squared minus 9. This is not a quadratic equation on the surface because to be quadratic, it has to have 2 as its degree, as its highest exponent. However, if I looked at x to the 4th as x squared squared, which I know I multiply when I raise an exponent to another exponent, I multiply, so that's x to the 4th, it's written in a new form, minus 8, and I'm going to bundle this x squared here as well, minus 9 equals 0. You can see how this fits the mold of a quadratic. It fits the mold of a quadratic now because now I have 2, 1. Just like I do with a regular quadratic, ax squared plus bx plus c. So what I can do is say, okay, well, I don't want to deal with all these squares hanging out everywhere. So I'm going to call x squared u. And I'm going to substitute u in wherever I see x squared now. So what my new equation looks like is u squared minus 8u minus 9 equals 0. This equation factors. I would take you through all the steps of using the AC method to factor, but we don't have the time, so I'm just going to factor it in my head. This factors to u minus, oh, no, wait, it does not factor. I got tricked because it's a minus on the inside. So we'll use the quadratic formula. And I'll just point out A, B, and C real quick. A is understood to be 1, B is negative 8, and C is negative 9. So, we have U equals the opposite of B plus or minus the square root of B squared. Oh, wait a minute. It does factor. That's going to be much quicker. Derp. Sorry. My brain's in summer mode. This factors as u minus 9 times u plus 1. Oh, that's so much easier. All right, so now we have our zero product property that we can use. U minus 9 equals 0. U plus 1 equals 0. So in this case, u is equal to 9. And in this case, u is equal to negative 1. Those are not our solutions, though, because remember we substituted. Now we're going to bring back in the fact that what we originally substituted for was that x squared was equal to u. So x squared equals 9. And x squared equals negative 1. Okay. So I can actually use my square root property here to solve. Take the square root of both sides. The original equation said, what can I square to make 9? Well, I can square positive or negative 3 to make 9. You have to take into consideration both those values. And when I take the square root of each side here, I end up with an imaginary solution. X is equal to, this is actually positive or negative I, so we're not even going to deal with that right now. We'll just go with the real roots. And so I've got two solutions, positive 3 and negative 3. All right. Same type of problem up to the right here. So here I'm going to call u x minus 5, that entire expression there. So I have u squared minus 4u minus 21 equals 0. The factors of negative 21 that add to make negative 4 are negative 7 and positive 3. There's a little insight on how to factor that. So u minus 7 equals 0, u plus 3 equals 0, u equals 7, u equals negative 3. So now I plug my expression back in that I substituted for. So I have x minus 5 as that expression that I substituted. So x minus 5 equals 7, x minus 5 equals negative 3. Here I'm going to add 5 to both sides, so x is 12. Here I'm going to add 5, so x is 2. I've got two solutions, 12 and 2. Last slide. solving rational equations, and this one's a doozy as well. Hopefully I'll finish before the next lecture starts. Goodness. So I have 3x plus 2 over x minus 2 plus 1 over x. I'm going to leave some room, and you'll see here y in just a second. Equals negative 2 over x squared minus 2x. Okay, so these are basically big, nasty fractions. And I have got to add them and subtract them. So I need common denominators. And what I'm actually going to do is go ahead and come back and delete that denominator and factor it. There's an x in both of those, so this is x times x minus 2. That gives us a little more insight. So to find a common denominator, I've got to make sure all of the factors that live in any of the denominators show up in all of them. So I have a denominator of x, and I've got an x here, so I'm good with that term. And I also have a denominator with a factor of x minus 2. I'm missing an x minus 2 in that second term, but I have it in this third term over here on the opposite side. That's why I factored it, to see what factors I was missing and what factors I needed. So my first term needs a factor of x. And I can't just go around and give it an x, but I can multiply by 1 as much as I want to. And x over x is just 1. Anything divided by itself is just 1, except for 0. This second term needs an entire x minus 2 factor in the denominator. So I'm going to multiply by x minus 2 over x minus 2. And my right-hand side is fine the way it is. All right. So just to point out, this is distribution that has to happen here. Here, 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 and here, here, and here, here, and here. And actually, I'm not going to distribute my denominator. I'm just going to leave the denominator factored, but I am going to distribute the numerator. And you'll see why here in just a second. X times 3x is 3x squared. X times 2 is positive 2x, and that is over a denominator of x times x minus 2. Plus 1 times x is x, 1 times negative 2 is negative 2, and that is over a denominator of x times x minus 2. And that equals negative 2 times x minus 2. Okay, so I can now combine the left-hand side to create one fraction. That's what I'm going to do. And to do that, I combine my numerators over my common denominator. And notice I have like terms that I can also put together. So now I have 3x squared plus 3x minus 2 over my common denominator of x times x minus 2. Negative 2 over x times x minus 2. Now I am at the point where I have a proportion. So I can multiply both sides by the denominators to get them out of there. Or I can do what we are familiar with as cross multiplying. So when I cross multiply, I get x times x minus 2 times 3x squared plus 3x minus 2. You only cross multiply across an equal sign. And then I have x times x minus 2 times negative 2. Now, this will be a sweet move for you here. You can divide x times x minus 2 off of both sides. And that leaves me with 3x squared plus 3x minus 2 equals negative 2. I'm going to go on to the next page to finish this up. Let me just take a little screenshot of where we are. And I'll paste it on this page. There we go. So we've got a quadratic to solve. And then we'll be done with this lesson. And that's good because I've only got about 10 minutes before the next lecture starts. Eek. I'm going to add 2 to both sides because I need to get that equal to 0. Actually, it goes away there too. And I'm left with 3x squared plus 3x equals 0. I'm going to factor 3x. Left over with x plus 1 equals 0, so 3x equals 0. Divide both sides by 3, x is 0, or x plus 1 equals 0, x is negative 1. There are your 2 solutions. You do need to go back and check them in the original equation because you're dealing with denominators. So let me go back. So we have 0 and negative 1. So we have x is 0 and x is negative 1. Oh, look what happens. If we plug in 0 for that x right there, it's going to create an undefined situation. Therefore, the entire equation becomes undefined. 0 is not a solution. Negative 1, we're good. The only solution is negative 1. And that's all I got for you for 2.6. Hope this was helpful. Let me know if you have questions.